if we call this theorem of Dirichlet the uniform version of diophantine approximation, because there's a uniform constant Q in here, bounding your approximation error. The next theorem due to Dirichlet will be called the asymptotic version of diophantine approximation. Instead of using this uniform constant Q, we're going to replace this by the norm of little q. But before we state this theorem, let us recall its version in the dimension 1 case. Let alpha be an irrational number. Then there exists infinitely many pairs PQ. PQ are integers such that Q is non-zero and PQ coprime, so GCD is 1, and you have this approximation error bounded by 1 over Q. This is the asymptotic version of the Dirichlet's diophantine approximation in the dimension 1 case. Namely, PQ are both integers rather than integer vectors. And now we are going to state its analog in high dimensions. So the theorem, let A be an n by n real matrix such that now we need an analog to alpha being irrational. What would be the analog of A being irrational in some sense? Alpha being irrational means alpha cannot be written as a quotient like A over B, where A, B are integers. Or in other words, any integer multiple of alpha cannot be an integer, except for the zero multiple of it. So here, the analog will be that if you apply A to any non-zero vector, you cannot get an integer vector. That is the analog of this condition in high dimensions. Then the theorem says there exist infinitely many pairs PQ in Z m plus n, where P is in Zm and Q is in Zn with 0 removed, such that First, we require that GCD of the components of P and Q to be equal to 1. And second, we can make the norm of the vector Q to be arbitrarily large. Remember this norm, we take the standard one, which is the maximum norm of its components. And thirdly, we have the analog of this in high dimensions. And this is the asymptotic version of Dirichlet's simultaneous diophantine approximation theorem. I believe you should be able to prove this theorem by yourself just from the uniform version of simultaneous diophantine approximation by carefully choosing this Q. I'll let you think about it on your own for a while, but I will give you the proof anyway. You might want to try it yourself first. Okay, now let me give you the proof. So first, for any Q greater than 1, you take P in Zm and Q in Zn as in the Dirichlet's simultaneous diophantine approximation theorem. Then you get the following two inequalities. For the uniform version. And furthermore, without loss of generality, we may assume, so without loss of generality, we may assume that the GCD of the components of P and Q is equal to 1. Otherwise, if the GCD is not equal to 1, then you just rescale P and Q. You just divide each component of P and Q by the GCD, and you still get the same inequality. Because in that way, you only shrink those parts. And now for convenience, let us denote the set of all those PQ satisfying this relation and this relation. Maybe let's call this 1 and this 2. PQ satisfies this 1 and 2. And we call all those vectors with PQ satisfying 1 and 2 the set script S of Q. As you can imagine, later you will see the script S of other parameters. And here's the idea of the proof. The idea of the proof will be to choose Q bigger and bigger. And we choose those PQs correspondingly. But the difficult question will be, how are you going to make this Q blow up? Remember, in our statement, we need arbitrary large values of the norm of Qs. When you choose Q bigger and bigger, how are you going to control that this Q has norm bigger and bigger, and the norm of Q goes to infinity? To this end, we must have a better understanding of how this Q will influence our choice of P and Q. If you just look at the second part of this equation 1, if Q is big, the norm of this will also be allowed to be big. But it doesn't necessarily mean the norm of this has to be big. So somehow the first line of this equation will play a more important role. So now we consider this set. The set of the values of this norm such that the pair P, Q is in SQ. SQ defined here. Those pairs satisfying the equations 1, 2. And now you look at the minimum or infimum of this set. Actually, there is a minimum, because if you fix capital Q, then there are only finite choices for P and Q, because they are integer valued anyway. In the statement of asymptotic version of Dirichlet's approximation theorem, we don't need less than or equal to in here, but the uniform version we proved above really states that, so this guy is less than or equal to 1 over Q raised to the power n over m. So we have to be consistent. But anyway, there are only finite choices of integer value. Okay, anyway, there are only finite choices for the integer vector P and Q. So we can take the minimum. If you look at this minimum, I claim that this is positive. Do you see why this is positive? I'll let you think about it first. It is positive because we assumed at the beginning that A applied to Z for any non-zero vector Z in Zn is not an integer vector. As a result, when you apply A to Q, with Q not equal to 0, this A times Q cannot be integer valued. So no matter how you take P to be an integer vector, this guy cannot be 0. Because there are only finite choices, the minimum will also be non-zero, which is positive in this setting. So I just talked through this claim without writing the proof, and you should be able to understand. Because this minimum is positive, what we can do is that we will choose Q1 greater than Q such that 1 over Q1 raised to the power n over m is less than this minimum. And now we're going to replace this script s of Q by the script s of Q1. And we claim the following. For any pair P prime Q prime in SQ1, we have the norm of Q prime is strictly bigger than the norm of Q. For any Q with PQ in SQ. SQ as in here. So why this is true? You should think about it on your own first. So you might want to pause this video for a while and think about why this is true. But I will tell the answer anyway later. So let me call this claim prime. And let's check the claim prime. Suppose, on the contrary, that there exists P prime Q prime in SQ1 such that the norm of Q prime is less than or equal to the norm of Q. What do you think will happen? What will happen is that because P prime Q prime is in SQ1, then it satisfies those inequalities. By the definition of SQ1. But remember, how do we choose Q sub 1? We chose Q sub 1 so that this guy is less than a minimum of this. Let me copy it down in here. This power of Q sub 1 is strictly less than the minimum of all possible such norms with P, Q in SQ. Then you get the contradiction. Why contradiction? Remember, Q1 is also bigger than Q by our choice. The contradiction is that because we could have chosen P prime Q prime in S of Q rather than S of Q1. Since if this is true, the norm of Q prime is less than Q. Because Q1 is bigger than Q, this norm will be less than 1 over Q raised to the power n over m as well. And remember, you can adjust your P prime, your choice of P prime, so that this guy is as small as possible. so that this guy reaches its minimum. So the contradiction is that this part contradicts to this inequality, because S of Q already consists of all possible choices of P, Q such that 1, 2 hold. If you are able to choose P prime, Q prime in S of Q, then you cannot make this to be strictly less than this minimum of all possible values for this norm. That is a contradiction. So this verifies the claim prime. This is maybe the trickiest part of this proof. I hope you can understand. And if you don't, please let me know in the comments. So if you understand this part, the rest will be easy. It will be just the induction. So now choose Q2 to be strictly less than Q1 such that 1 over Q2 raised to the power n over m to be strictly less than the minimum of those norms AQ prime minus P prime with P prime comma Q prime living in S of Q1. And the same argument shows you that for any P double prime, Q double prime in SQ2, you have the norm of Q double prime is bigger than the norm of Q prime. For any Q prime with P prime, Q prime in SQ1. So this procedure will move on. In the end, you get a sequence PV, QV in SQV for any positive integer v, and the norm will be in a strictly increasing order. And this strict inequality means increment at least 1, because those norms are integer valued, since those vectors are integer valued. So you know this guy will go to infinity as v goes to infinity. And this fulfills the second requirement of our theorem. The first requirement is automatically fulfilled because our construction of SQ. In our construction, already required that the GCD of those components is equal to 1. So now it remains to see why the third statement holds. The third statement holds simply because of our definition of SQB. Remember that this means the norm of AQB minus PB which is 1 over QB raised to the power n over m, and the norm of QB is bigger than 0 and less than QB. So the second part will imply that this guy is strictly less than 1 over the norm of QB raised to the power n over m. And finally, we proved the third statement and thus the whole theorem.